Hello, let's talk about rotational motion. So our goal in looking at these chapters in our book is to make this motion from translation, which is something moving in a straight line, basically, to rotation, something moving, either in a circle or spinning like a top, which is clearly what that's trying to do. In general, most of the physics that we're going to encounter is delightfully similar to the physics we have been doing. So just like before we were doing kinematics involving position, velocity, acceleration, and time, we are going to find that there are rotational kinematics, which will involve, instead of displacement, it'll be angular displacement. Instead of velocity, it will be angular velocity. Instead of acceleration, it will be angular acceleration. Instead of time, it'll still be time. This I should point out in case we're not up on our Greek. This is in lowercase omega. This is a lowercase alpha. And that is angular velocity, angular acceleration. Now, instead of mass, which we're thinking now in terms of an inertial mass, a resistance to motion, so Newton's laws style, we're going to have a rotational inertia. We'll get into this more, but it's basically just as mass is the resistance, not inertia. That's something totally not existent. Just like mass is going to be the measure of how difficult it is to accelerate something, rotational inertia will be a measure of how difficult it is to angularly accelerate something. And then instead of talking about forces, we'll talk about torques. And we'll go into all of these in some greater detail as we continue. So, let's look at some examples. We define velocity as the rate of change of position. Delta x over delta t, or in a calculus sense, dx dt. Angular velocity we'll define in an almost identical manner. We'll replace the linear variable with the rotational variable. So angular velocity will be the change in the angle over the change in time, or the rate of change of angle in a calculus sense. Alternatively, something like Newton's second law, which will be F equals ma, will go to its rotational equivalent, that the torque is equal to I alpha. Every rotational variable steps in for its linear cousin or nephew, not nephew, that'd be really weird, sibling, twin, parallel universe-ish thing. You get the idea. This means from a functional level, every problem we will do employs the same basic problem-solving techniques as every problem we have done. There are just a couple of different caveats, which are largely going to arise from talking about torque and rotational inertia, but we'll get into those in a second. First, let's think, where are these coming from? Try to justify their existence. This, recall, is kind of our definition of arc length. It's one of those things that kind of we assume that you learned, and I don't remember when I formally learned it, but I always think of it in terms of, that circumference is equal to 2 pi r, because the circumference is, 2 pi is all the way around the circle, and a circumference is the distance all the way around the circle. So for some arbitrary step along the circle of an angle theta, you get an arc length s. So we're looking at something like this. We have here our circle, radius r, and you step over some arc length s, carving out some theta. So ds dt is then my linear velocity, right? This is how fast I'm walking along the circle in terms of the distance I'm carving out. Is going to look like ddt of r theta. Now for a circle where my radius is constant, dr dt is 0, so this is just r d theta dt, which is r omega. Keep in mind that's the definition we were talking about just a second ago. So the idea of this is that for a given angular velocity, you might have many linear velocities. The closer you are to the center of a circular path, the less rapidly you are moving in a linear sense, even though you are carving out the same angle in a given time. Which, incidentally, if you think about it, probably means that the linear density of information in a record or a CD has to vary, since the speed of the disk is probably kept constant. Well, it is kept constant in the case of a record player. I guess you could... Anyway, neither here nor there. Sorry. Similarly, A equals R alpha. In general, these are all related by a factor of length, which you can think of because in terms of dimensional analysis, a velocity is going to be meters per second, but an angular velocity is going to be radians per second. So there's a factor of length difference between them. Now, let us come to some important things. What is I? I is referred to as the moment of inertia, as the rotational inertia, or as the second moment of inertia. It's the second moment because the center of mass would be the first moment. It's mass times the first power of displacement. This is mass times displacement squared in general. So in the discrete case, for a whole bunch of masses, all a distance r, so these are masses m. R in this case is the distance from the axis of rotation. Distance, I can spell distance. Technically it's the perpendicular distance, but that distinction almost never, from axis of rotation, never really comes into play. Just like when we're calculating center of mass, we're summing up mr in that case. This case we're summing up mr squared. We don't care if it's the left of the center, to the right of the center, in front of the center, behind the center. We just care that it's away from the center. It turns out that it is harder to spin an extended object than it is a narrow compressed object. When we get to angular momentum, we'll really drive this home as we think about how your angular velocity changes if you change your rotational inertia, just like you can think of how your velocity changes if you change your mass. Similarly, for a continuous distribution of mass, this will be an integral over dm. So, an example of this. Consider, if you will, a hoop of mass m and radius r. This mass is spread over the entirety of the hoop, so I'm thinking of this. I need to get it, in order to do an integral, in terms of a coordinate. So theta is going to be the coordinate I take. It's a uniform hoop, so it's spread over it's spread over an angle of 2 pi. So the little mass over the little angle would be the total mass over the total angle. This is in general how you set up that kind of differential relationship, by the way. Useful information. So this would be my expression for rotational inertia, which I can then plug in what dm will be. R for each of these is going to just be the radius r. It's all the same distance away, which is great. So this will just look like mr squared. This is the only example that the AP exam will generally expect you to know off the top of your head, because it is the simplest example. All of the mass is one distance away. They will expect you to be able to combine this with point masses. So maybe it's this and then like a mass here, some distance, little r. And I would just add these up then. So that new one would be mr squared for the hoop plus mr squared, let's say this is m, for the little dot which is hanging out in space but somehow also spinning when I spin the hoop. Who knows? It's one of the mysteries of life. There's one other thing that you need to be aware of when you're doing this, and this is the parallel axis theorem. And the idea with the parallel axis theorem is that if I have an axis through this hoop through the center of it, and I know I can spin around that axis, that's great. That is going to give me this moment of inertia here, I-C-O-M. What if instead of rotating about that, though, I wanted to rotate like I'm doing kind of a cool hula hooping stunt where I have it spinning around my toe? So it's going to rotate around a point here on the edge of it. So I need to shift the axis by some distance. Let's call it h. That is what this term is. It allows you to shift the axis of rotation to a second axis parallel to the first by adding this term. Your book goes through a proof of it. The proof is not terribly important, but this will pop up from time to time as a useful shortcut and way to reframe a situation. The other thing that we want to talk about is what is torque. So a short answer. A torque is a force applied some distance from the axis of rotation. A shorter answer is that it's r cross f. A shorter answer without a cross product is that it's rf sine theta. All of these are meant to try to tell us that a torque depends on how much force you apply. It depends on where you apply it, and it depends on the direction of application. So when we're looking at this is the magnitude of the cross product over here. What it's meant to tell us is that a given torque will be greater if it's applied, further from the axis of rotation, which I should probably point out that's the distance from the axis again. It'll be greater if the force is greater. just the applied force here. And it'll be greater when sine theta is greater. So sine theta is greatest when theta is 90 degrees. So theta in this case is the angle between the displacement from the axis and the applied force. So consider a door viewed from above. So here is, the hinges here maybe. There we go. If I'm going to push the door at this area, this would be the optimal way to do it. Here is my displacement vector r, here is my force F, and there's a 90-degree angle between them. You would find that there is no force if I were to say push the door or no torque rather, if I were to push the door in this direction. That is a bad choice. One way to know this is you may learn just by practice that the cross product of parallel vectors is 0. Or if you look, simply I'm not going to rotate the door if I'm trying to pull it to the side. So a general rule of thumb when we're looking at these is that we need to think, the more mass is spread out, the harder it is to move something. That is what that this idea of rotational inertia is trying to tell us. That, as for a given mass, the more spread out it is, the greater the effective radius of it, the harder it is to rotate it. And then, similarly, for a given torque, the further away you push it from the axis, the easier it is to rotate it. So we now have to kind of worry about the spatial arrangement of our forces and of our objects, and that is going to be the major big change in dealing with these problems. So hopefully this gives you a good starting point for dealing with rotation. And just trust the skills you've developed in the last couple of chapters in terms of reading a problem, and just add on this one extra bit of worrying about now the shape of it. Good luck. I can't remember the command to end this. I hope I can edit this out after.